All right. Once again, a reminder about the tests coming up tomorrow. It's covering chapters 22, 23, and 24. 22 is about magnetism and magnetic force. So we learned about two things that will cause magnetism. What are the two things that will cause magnetism? Only one of them was actually in chapter 22. The other one was in chapter 23. But
wasn't one of them like movement of a current?
Okay, a current flowing or moving charge. You combine both terms together, or both. A moving charge or a current will create a magnetic field. The other one was something intrinsic. It's the magnetic moments of the constituents of the atoms. So we have two different ways that we can create magnetism. And with that second one, we saw things like a magnetic material, of which there are three types. Ferromagnetic, which is usually what we mean when we say magnetic material. Ferromagnetic is strong magnetic, like iron, and it has little magnetic domains in there, regions where all the little magnets are aligned together from the atoms. And if you put a strong magnetic field, you can make them align with the external magnetic field. It turns out this is really useful in things like geology. Sailors traveling over the ocean noticed that their compasses were doing funny fluctuations. And so scientists, first thing in science is you know something interesting, they go out to study it. And what they found is that the bottom of the ocean floor behaves like a magnet, but the direction of the magnetic field is changing. And our understanding is you have molten magma that comes up to form the ocean floor, and it freezes with its little magnetic domains aligned with the Earth's magnetic field at the time it froze. And so what we have on the ocean floor is a magnetic history of the ocean floor, storing those magnetic domains. Then we had the force between magnets. We have the force opposites attract, likes repel, or that there's always a torque to try to make magnets align up with the field. So magnetic field comes out of north, goes into south, and does loops. Repeat what? Either by having a current flowing, that is moving charge, or an intrinsic property of atoms, because atoms are made out of protons, neutrons, and electrons, and all of those behave like tiny bar magnets. They have a magnetic moment. So in terms of the force between two magnets, we don't have an equation that we used for that. All we have is there's going to be a torque to make the magnets align together, and that opposites attract, likes repel. Magnetic field lines always go out of north into south, forming closed loops. But then we had the force between a moving charge and a magnetic field. That we had an equation for. Force equals QV cross B. So let's just do a simple example of that to make sure we know how to find the direction. What does a cross product mean? You're multiplying the perpendicular parts. So if I have a magnetic field that here is pointing, okay, let's be realistic, that direction's north. Pointing like this, let's say 45 degrees below the horizon in a northerly direction, with a strength of 0.5 Gauss. And I have an electron going in this direction. How do I find the direction of the force on that electron? The right-hand rule. So what direction should I put my index finger?
The direction of the current.
The first one, in this case, it was QV rather than IL. So the velocity of the charge. So my index finger goes that way. And then how do I orient my hand after that? Middle finger can point direction of the magnetic field, so I have a middle finger like that, and then my thumb points the direction of V cross B. But I said it was an electron. So the electron, because the negative charge can be opposite. Okay, seems like you guys got that down. That's,
like as a group, we have it down.
as a group.
Individually, a little less so.
If it had been a wire with current going the same direction, There's only one thing that would have been different. You wouldn't have reversed if it was current going that direction. Because you don't have a negative current, you have the current. Right? Because it's IL cross B. If the current's going like this, your index finger does that. Middle finger, that. And force is it. Okay. Yeah. One of you two has a question.
Oh, we have four questions. So it's only reversed if it's electron, correct?
Right. You only have to worry about it because the I is always going to be a magnitude and the L is the direction that the current was going. So you only have the reversal option if it's charged. What's your question?
How do you know which direction the magnet is?
In my case, it was given. I said that I specified that it was a 45-degree downward in the northerly direction.
Yeah, I was looking. I can see where you're going. Okay.
Okay, was there other question, Maxwell?
The 45 degree, that was in the field, right?
Yes.
And the finger would be
Well, my index finger was the direction of the velocity. My middle finger was the direction of the magnetic field. My thumb then was the direction of V cross B. And since I'm multiplying V cross B by a negative number, Q, then it reverses the direction to that way. Now, as I've said many times, on the test, you are going to have to do a problem with the right-hand rule. Remember that your paper can move. You don't need to be trying to do this with your arm. Just rotate your paper, mark on your paper according to how your hand is when you figure it out, and then rotate your paper to normal and figure out what you just did. I'm not sure what you said. I think it did, but I'm not sure what you said, so I can't.
Instead of flipping the paper.
Oh, well, I'm just talking about having your hand so it's twisted up funny. Just so you don't have to be contortionist during the test. Yeah, right. Okay, so chapter 22, those are the main things. So once you have the forces, you still have to remember how to add forces as vectors and that kind of thing. Chapter 23, magnetic induction. Now, we did have in there Faraday's law of induction that says that the current makes a magnetic field, and so you need to have your basic rules. If I have a current that's going from me to Maxwell, what direction is the magnetic field that it creates at the ground between us?
That one.
Okay, Andy did it exactly right. Pointed her thumb in the direction of the current, and then oriented her hand so her fingers were below, because the ground is below the line connecting me and Max. Fingers were pointing that way, and so at that point, going that direction. Then the magnetic field is going to be doing circles around the wire, and use that right-hand rule, the thumb the direction of the current, fingers direction the magnetic field wrap around the wire. Okay, the final one for right-hand rule is if you have magnetic field going in a loop. So let's take, for instance, suppose magnetic field is going around this split ring. But let's pretend it's going, or magnetic field, current is going around this ring. Then I take my right hand and I wrap my fingers the direction the current is going on the ring, and my thumb points the direction of the magnetic field in the center of the ring. So the magnetic field is going to come out here and then go in on this side, outside of the ring. So I wrap my fingers the direction the current's going. My thumb points the direction of the magnetic field on the inside. So my thumb was pointing out, so the inside of this loop would have magnetic field coming out. But since magnetic fields make loops, it has to come around. So outside would be going the opposite direction.
That's like the coil, right?
Yes. Yes. A loop, a coil, same rule. You'll need to be able to calculate the magnetic field caused by a wire. That's just mu watt I over 2 pi r, equation on the equation sheet. Or the magnetic field by a loop, mu watt I over 2r, another equation on the equation sheet. Or magnetic field from a coil, mu watt I, times the number of turns divided by the length of the solenoid. Chapter 24, electromagnetic waves, which basically can be summarized in this picture. Yeah.
Do we need to know how to convert Gauss to Tesla?
You don't have to know that factor of 10 to the minus 4. If I don't have an equation sheet and you need to just raise your hand, okay?
Okay.
Because that goes in the term memorization. We don't memorize the facts. We need to memorize how things work. or commit to memory in a more working sense. Electromagnetic waves, we have Gauss's law, two laws actually. Gauss's law that we used in class that says that a charge makes an electric field. Gauss's law for magnetism that we didn't use at all. Then we have Faraday's law of induction, which you do need to be able to use from chapter 23. Faraday's law of induction about inducing a voltage or inducing an electric field depending on your situation from a changing magnetic flux. And remembering Lenz's law that the induced, and we went over this on Friday, I think fairly well, the induced magnetic field is going to oppose the changing flux. So that law, and then finally, Maxwell's addition to Ampere's law that says not only does a current produce a magnetic field, but so does a changing electric flux. And the changing electric field flux creating a magnetic field, the changing magnetic flux creating an electric field, provided the basis for waves. That you can make waves with alternating electric and magnetic fields. And the waves have to have the electric field perpendicular to the magnetic field and both of those perpendicular to the velocity. There's no, the right-hand rule, the first two didn't have to be perpendicular. It's just the third one had to be perpendicular to the first two. In this case, all three of them have to be perpendicular. And so based on this equation right here that relates the strength of the electric field and the magnetic field to C, as I will have in today's lecture, is the speed of light in vacuum. Which scientists decide, I'm sure there's one extra letter somewhere in there.
I think they use.
Only one C, two U's. Which scientists decide is equal to exactly 2997992. Oh, my brain's going soft on me. Yeah. That many meters per second. I contend if I would have been on the committee, I would have voted for 300 million meters per second, and that would change the meter ever so slightly. But they didn't want to change the meter by 2 parts in 1,000, so that's the number. So if we use this equation, then we should have E is equal to B cross C is a true equation. B cross C, yeah. So electromagnetic waves, those you're not going to do calculations from chapter 24, but you're going to do calculations from chapters 22 and 23. I already reviewed this once, but is there anything you want to ask about the test before we move on? You can do it. Yes, I'm sure.
How much RLC circuit is going to be on the test?
How much? I thought RLC was on the last one, wasn't it?
Yeah, it was
I thought it was on the last one. Was it not?
on the last review.
No, the test was. Oh, you're right. It wasn't because we had inductors. It wasn't because we didn't have inductors yet. So yes, there is RLC circuits as well. It won't be a heavy emphasis because all we did on it was in the lecture and then the abbreviated lab. Yeah, we put off transient circuits and we hadn't gotten to RLC circuits for the last test. And we're not going to have transients. Maxwell.
Is there a worksheet for chapter 24?
I thought so.
Yeah, they're up.
Yeah.
There's not going to be an equation though.
Right, you're not going to do calculations. So there's a calculation there. You're not going to have to do a calculation. Although there's questions in the problem, you should know the answers to those questions. All right. Homework number 4, according to what Sarah asked me, is similar to this. I told you I would do this problem at the beginning of class today. And I told you, if that problem is difficult for you to hold off on it after class, it'll be much simpler. So the question is, what is the deviation angle? So I have light that comes in. This is my incident ray. Light that comes out here and reflects off of 2 surfaces. Now I am going to arbitrarily name this angle gamma. The problem here was if it's a 90-degree angle for gamma. But I'm going to do it just with the generic gamma. You know why? Because that means that my work will be the same work as you have for your homework problem. It's just generalized instead of being specific to 90 degrees. What I need to do is to calculate how much it deviated at each reflection. So the straight path, come on, the straight path would have gone like this. So the amount it deviated for the first reflection is this amount here. And so using my geometry knowledge, I know that the angles going from one side to the other side of a straight line have to add up to 180 degrees. And so if I just look at this picture, theta 1 plus delta 1 has to equal 180 degrees.
Does the gamma one also have to equal theta 2 plus theta 2?
I'm actually going to get to that. There's a relationship there, but I'm going to do that third. That's my planned sequence here. Okay, so now I'm going to look at theta 2. So if it came here, this would have been the straight line. So the deviation there is, by the same rule, theta 2 plus deviation 2 equals 180 degrees. Now I'm trying to find the total deviation, and so my total deviation is deviation 1 plus deviation 2. So I'm going to take the two equations that I just got and add them up. Actually, I'm going to erase this and move it somewhere else so I can add them without a problem. So if I add these up, 2 theta 1 plus 2 theta 2 plus deviation 1 plus deviation 2 equals 360 degrees. Or simplifying this a little, 2 times theta 1 plus theta 2 plus the total deviation is equal to 360 degrees. So if I can find what theta 1 plus theta 2 is, what Andy was directing us to, then I'm done. So how do I find what theta 1 plus theta 2 is? There's more than one way to do this. I have my favorite way. You may have a different favorite way. I am not going to argue with somebody about which way is better. So what I'm going to do is complete this rectangle. Well, it's a rectangle in this picture. It wouldn't necessarily be a rectangle with other pictures. These were the surface normals, right? Angle of incidence and angle of reflection are measured from the surface normal. So I know those two angles are 90 degrees. What's the sum of the interior angles of a four-sided shape? 360 degrees. So I have the sum of the angles equals 360 degrees for a four-sided shape. What would it have been for three-sided? 180 degrees for three-sided. And I'm not going to go through what the other shapes are, but both of those are important when you're doing geometric optics. So in this case, I have a four-sided, so I'm going to have 90 degrees plus gamma plus 90 degrees plus, and let me just call this alpha. Oops, that didn't write. So there's an equation that relates that angle alpha. I am going to simply solve that for alpha. So if I subtract 90 twice, 180 degrees minus gamma. And finally, sum of the angles for the triangle. So using the triangle that I make with that same angle alpha, alpha plus theta 1 plus theta 2 equals 180 degrees. Therefore, theta 1 plus theta 2 is 180 degrees minus alpha equals 180 degrees minus, parenthesis, 180 degrees. Did I do all that right?
I think so.
What was that? Yes. No. This or up here, 360 degrees minus 90 minus 90. Something feels off about this because it should be, well, alpha is not equal to gamma. Where did I make a mistake, friends? No, the answer is supposed to be 180 degrees minus gamma, and I have 180 degrees minus 180 degrees minus gamma. Alpha plus theta 1 plus theta 2. Oh, no, that's correct. That's correct. It's equal 180 degrees. Now it was 90 plus gamma plus 90 plus alpha is 360. So plus 360. The sad thing is for my 90 degrees, it turns out right, but that's two wrongs make a right. I worked this out before class without a hitch, and it's just a minus sign somewhere, but I want to know where it is. Actually, wait. No, it's okay. I was thinking I was getting to this one. There's no mistake except for me not realizing which part of the problem I'm in. So theta 1 plus theta 2 is equal to gamma. Everything was correct.
Can you see that with your second?
So now I'm ready to answer my question. What's the total deviation angle? So there's the total deviation. So if it's a 90-degree angle, the deviation is going to be 360 degrees minus 2 times 90, 360 minus 180, leaves you 180 degrees, which means that it comes straight back the direction it came from. Offset a little in position, but going opposite direction. In your homework problem, you just had a different angle here where I put gamma. And so you're going to have a different deviation as well. Now, what it asks you for may not be what's the deviation angle, so you have to make sure what it's asking for is what you calculate, but that gives you how much it deviates.
I guess my question is like, because like when our flights off the meter, are you talking about like exact angle of reflection, or is that like the same what is not clear?
Okay, it says off the mirror net, so it's off the second mirror. It makes an angle of 10.5 degrees. So you're talking about, oh, I thought you were talking about 12. Maybe not. What did you ask me? So this here is giving you what theta 2 is. The 10.5 degrees is theta 2.
Right.
And so you're,
Is that the angle of reflection, or is it the actual angle of reflection?
the angle of reflection is the angle of reflection.
Not the angle of reflection.
Or excuse me, yes. It makes it the normal, but yes, unless it shows otherwise. It should be.
I guess it should be that, right?
Yeah, it should be that. That's impossible? Let's bring it to me after class. Okay, so geometric optics. We're doing a lot of geometry here. It's part of the reason that college algebra is required for this class, because you learn some geometry there, not a lot. It would be better if we had pre-calculus where you have trigonometry included. So we've learned about the two types of reflection. Specular is listed here. What's the other type of reflection?
Diffuse.
Diffuse.
I was like, it's the one where you can't see the reflection.
Right, the one that you can't see a mirror-like reflection because the surface is on a microscopic level rough, and that's diffuse. There is a third type that we simply don't have to know about, and that's called phase conjugate. If you have light hitting a transparent material, by definition of transparent, most of the light goes through. If it's glass, typically about 4% will reflect. So, like right now, I look at Max's glasses and I see a reflection of the light off of his glasses, what we call glare. That's about 4% of the light that was reflected off. The other 96% went through so Max could see the light. So for the most part, we're going to ignore this 4%. We will bring it up a time or two, but for the most part, we're going to ignore it. And we are going to simply look at the transmitted light and figure out what happens. So we've already learned about wave fronts. Remember, we had the water wave, and I was showing the wave fronts and whatnot. And the wave fronts are separated by one wavelength. Well, if we have light going, okay, I'm going to actually open up that in a minute. If we have light going from one material into another material, the speed of light changes. The speed of light in water is much slower than the speed of light in air. And because of that, the light changes direction. We call that change in direction when you go from one material to another refraction. So reflection is bouncing off. Refraction is transmitting and changing direction because you went to a new material with a different speed. So I'm going to go to this lower link, and I already have it open here. This lower link shows you a wave coming in. So I have a wave front. That's just a single wave front. And it's going to go from medium 1, which is set to index refraction of 1, to medium 2 with index refraction of 2. And it doesn't show anything happening. I have to go to the next step. Next step. Now it's going to go in, and it's going to start a new wave when it hits the surface following Huygens' principle. So you see those waves that are coming out. Huygens' principle says I can take any, okay, and I have to say this because it kind of cracks me up. When I was a student your age, I learned the name was Huygens' principle. In graduate school, I learned Huygens' principle. I was looking at a guy explaining this on a website, and he said, Huygens or Huygens' principle. I was like, okay, now this is getting ridiculous. His name in reality is Christian Huygens. And in America, we typically say Huygens. And in England, they typically say Huygens. So go with the one you like, but it should be something like Huygens or Huygens, not Huygens or Huygens. And there's an S in the end. His name was Huygens. So this here is the next to pay off. We have a wavefront come. Oh, wait. Yeah, I hit next step. Should have worked. We have the wavefront coming in. It's making new waves along the surface. Huygens' principle, yeah, I started saying it didn't finish. Huygens' principle says that for a wave, you can take any point on the wave and treat it as a point source for a new spherical wave. And so when it hits the interface, it's starting a new spherical wave at the points shown, take those as the point sources. And it shows us how those add up. And so the key to what you see here in this one, and I'm just going to go to the next one because each one's adding on a step, is that you have the wave fronts moving. The line here is the incident ray, the direction the light is traveling. And then it creates these new wave fronts that reflect, following the law of reflection's angle of incidence equals angle of reflection, but refract in a different direction. And so then we use geometry to figure out what that direction is. Now I have a couple of slides to actually work out the geometry, but this was to remind me to go there. But instead of working out the geometry, I'm going to kind of jump to the chase. Something that's important when you go from material to another, the frequency stays the same, but the speed doesn't. The speed changes. So remember, frequency times wavelength is equal to the speed. Excellent. Frequency times wavelength is equal to the speed. Therefore, the wavelength is equal to the speed over the frequency. If the frequency changes or stays constant, but the speed changes, then the wavelength must change. So the wavelength, when we change materials, changes. And in another slide, 2 slides, I'll show you the calculations of how we do a very quick calculation for the change in wavelength. So frequency stays the same is important. If you have light that has a frequency of, let's say, 7 times 10 to the 14 hertz, and it goes from air into water, it remains at the frequency of 7 times 10 to the 14 hertz. But its wavelength is going to change. So here's the picture for geometry. Like I said, I'm going to skip over the derivation for the sake of time, but point out this important thing. N stands for index of refraction, and it's defined as C, the speed of light in vacuum, divided by V, the speed of light in whatever material you have. So next slide, I'm going to do a problem. Slide after that, you're going to do a problem. And we're going to calculate the speed of light in different materials based on that relationship. So speed of light in vacuum, a fixed number, that's constant. And in any material, we identify this index of refraction as the speed of light in vacuum divided by the speed in the material.
What's that again?
N is the index of refraction. Something that's important, light, the speed of light is always slower than or equal to the speed of light in vacuum. And in fact, if you're not in vacuum, it's always slower. So V is always, unless you're in vacuum, if you're in vacuum, C over C is 1, then it's refraction for vacuum is 1. If you're not in vacuum, C is always bigger than V, which means the index of refraction is always bigger than 1. So index of refraction is always 1 or greater. This here is, if you want to follow the geometry, you can. It's relating these 2 triangles to give us what we call Snell's law. It says the index of refraction in the first medium, incident medium, times sine of the angle of incidence in the first medium is equal to the index of refraction in the second medium times sine of the angle of refraction in the second medium. Keep in mind, very important, those angles are measured from normal, not from the surface. If you try to do it from the surface, you will be absolutely wrong with refraction calculations. With the reflections, it would have been fine if you'd done it from the surface. With these, it won't be fine. So, simple rules. If you go from a faster medium into a slower medium, that means N transmitted is greater than N incident, then it's always going to deviate toward the normal. It's kind of like, my example is, I can ride a bicycle faster on cement than I can on sand. And so if I'm riding in one of those little carts at the beach, 4-wheeler, and 2 of the wheels go into the sand, it's going to jerk me so I'm heading more into the sand. I'm not going to go straight. I'm going to bend toward the normal of the interface. That's exactly what happens in light for the same reason. Because it's slower in the new medium, it bends toward the normal. Light also works the same forward and backwards. So if the light was coming this way, it would refract away from the normal. So now it's time for me to work a problem so you can see it in action. So, diamond. Diamond has an index of refraction of 2.42. First question, what's the speed of light in diamond? Slow. Slow compared to in vacuum. fast compared to anything else. Index refraction is defined as speed of light in vacuum over speed of light in the material. So that means V is equal to speed of light in vacuum over 2.42 or over N equals 2, let's just between friends say 3.
Are we going to be using 3 from here on out? Or is it
And unless you need more than 3 significant digits. To 3 significant digits, it's 3.
Okay.
To 4 significant digits, it's 2.998.
Are there units for that?
For the index refraction, no, because C and V both have units of meters per second, so they cancel. So yeah, I'm just going to let Anna divide this out for me. What is V equal to?
1.23 times 10 to the 8. 1.24 times 10 to the 8.
So it's going a fair amount slower than light does in vacuum. That's part of the reason diamonds are special. Diamonds are hard, that's another reason they're special, but that's not why you put them on your ring. You put them on your ring because of the very slow speed of light in diamond. With that slow speed of light in diamond, when you do this diamond cut, you have light comes in, reflects across, and comes out with no light lost. So any light that comes into that top facet comes out of that same facet, actually not the same facet, it's off the side, and comes back at you. Now, if it's poorly cut, you may lose some light inside. So here's some light lost, here's some light lost. Or it may go out away from you instead of coming back toward you. But the diamond cut is actually very carefully calculated to make it so the light comes back at you. Now, there's some things in here that are not things we've studied yet. When the light hits right there, it reflected. It had what we call total internal reflection. And we'll learn about that in lecture on Wednesday. We're not going to get to that today. But that is also a function of the speed of the light in the diamond, so that the diamond is going to have total internal reflection a lot more than like glass would, which means you're going to get a lot more of the light reflected back out at you than you would if it was glass. Oh, wait, there was a second question there. What is the angle of refraction if the incident angle is 30 degrees? So here's my diamond interface. Here's my incident ray. Where do I measure the angle of incidence from? From the normal. So I'm going to draw the normal on here. I usually do it as a dashed line. And so here it's 30 degrees. And then what direction is it going to refract? Toward or away from the normal? Toward, because diamond is much slower. And so I'm looking for this angle here. And I have N1 sine theta 1, I'm using 1 and 2, equals N2 sine theta 2. I'm looking for theta 2. So the first thing I have to do is divide both sides by N2. That gives me sine theta 2 is equal to N1 sine theta 1 over N2. And now I get out my calculator. N1 since this is air, I shouldn't put equals air. Air is 1.00 to 3 significant digits. Air is very close to vacuum. So you don't have to look that one up. And 2 is
what was given in the problem, right?
in this case, yes.
Okay.
And so when I put in those numbers, sine theta 2 is equal to 1.00 over 2.42 times sine of 30 degrees. Sine of 30 degrees is 1/2. That's something, I don't know about you guys, but I think I told you I had to memorize that when I was in high school. How do I get theta 2 now that I know what sine theta 2 is?
Arc 2. I mean arc sine.
So theta 2 is equal to a sine of 1.00 over, I just multiplied through 4.82. And somebody have that in a calculator, or should I do it?
Oh, I got 11.9 degrees.
11.9? Because that's 2. Should be 4.84. Because apparently I can't multiply by 2.
I can't
Hold on.
It-
What?
I did 2 times 2.42 was 4.82 instead of 4.84. That was
Well, let me check on that, because I think I did something slightly different, but then-
it. Probably going to come out right. I'm just trying to do as much in my head as I can. All right. Also,
So, in one, because it's air, it's always going to be.
yeah, if it's air, you can have a case where it's going from water to glass or glass to water. Then neither of them is going to be 1. Now your problem, which is actually a simpler form of this, a beam of light strikes one face of a window pane with an angle of incidence of 30 degrees. Then its refraction at the glass is 1.52. Beam travels through the glass and emerges from a parallel face on the opposite side. Ignore reflections. What's the speed of light in glass? Find the angle of refraction for the ray inside the glass, and then show that after it comes out of the glass, it's parallel with the incident ray. That's the incident ray from the problem. Yes, yes.
You got the ones? What? What is that? Oh, well.
Oh, no. Even though it doesn't say air, are we assuming that it's air?
Yes, yes.
Jeez. I'm just so efficient. Whatever. I've always been copied.
Somebody got
Which
something.
one? See? Oh, because it's traveling through glass, because it's traveling through glass. Because it's traveling through glass, it's gonna be reflecting the opposite direction on the other side.
Wouldn't it be like boom, boom, boom?
Yeah, it's refracting the opposite direction. So like, when it goes through the glass, it refracts this way, and then when it passes through, because it went that way before, it reflects the opposite direction going out.
Here's what David said, because I think it's the same as what you said.
Yeah, it is.
We're saying the same thing,
Yeah.
just in very different words.
And of course, my artistry is always suspect.
Oh, it's like my drawing.
Those are supposed to be normals.
So just like final numbers.
Yeah.
Silly me.
I mean,
That doesn't say.
The part B says to find theta 2,
Okay.
and part C says to find theta 3, in essence. Because if theta 3 is equal to theta 1, then they're parallel. If theta 3 is different than theta 1, they're not parallel. Counting Claudia, has everybody finished part A?
Yes.
How about part B? How many are done with part B?
Yes.
Yeah,
I
couldn't figure out how to do inverse sine on the calculator.
So
So-
I need to
you can use into sign theta two.
Easy way out.
In three.
I'm think that this is theta 2,
Okay, that agrees with him, so that's good.
theta 3. I don't know. And it should just be theta 1, right?
That's what we're checking to make sure, yeah.
Oh,
No, but you're having to find
I'll
it.
check on that.
I'll get back to it.
Because it's on the side of the rule.
Yep.
Right?
What did you get from me?
Nothing changed, it was just like.
Yeah.
Flipped.
Yeah, actually, yeah, you guys, it can't be 50,
Why not?
because it's gotta be less than 30.
Why would it be less than 30?
Because it's
being
going into
refracted
a slower medium.
Could be 91 versus 40. What is the guess over here?
Yeah. Okay, so I think pretty much everyone has A and B done. There might be some mistakes, so let's just do them now. So A, V is equal to C over N is equal to 2.9979245 times 10 to the 8 meters per second over 1.52, which is equal to 1.97 times 10 to the 8 meters per, yeah, because we only have two sig figs. Yeah, me putting all of the digits is overkill. Then for the second part, we have N1 sine theta 1 equals N2 sine theta 2. So theta 2 is equal to, I'll put inverse sine because that's what Max's calculator had. N2 sine theta 2 over N1. Excuse me. I got my 1s and 2s all crossed. So inverse sine of that, which my calculator wouldn't do. What did you get, Sarah?
For the sign,
For theta 2.
19.
19.2 degrees. That sounds reasonable because it's less than 30 degrees. I didn't verify it, but it sounds reasonable. Now, the final thing, the reason I'm solving this now, instead of letting you go for the last 2 minutes,
Why are your angles from the inside?
they are, the pane is purple.
Oh, okay. I thought you were normal.
This is the glass here. Usually I actually put the ends.
You suck, you know.
So in this case, what's the relationship between my angle here and theta 2? They're the same because these two normals are parallel. And so the same line crossing parallel lines, same angle. And so what I have here is N2 sine theta 2 equals N3 sine theta 3. But N3 is the same as N1. And so if I refer back to this equation without doing any calculations at all, this side here is this side here. This N1 is this N1. So sine theta 1, I wrote theta 1 says theta 3 because I was jumping ahead. Theta 1 must be theta 3, and thus they must be parallel. All right. We will have an exam tomorrow at 2 right here. I believe that you are ready.
I don't have time.